In this video, we will be going over how to divide radicals. So it is generally agreed that a radical expression is not in simplest form if the denominator contains a radical. For example, 1 over the square root of 3 is not simplified because the denominator contains a radical. We will need to find a way to eliminate the radical from the denominator. And this is done by a process called rationalizing the denominator. So to rationalize the denominator, we use the fact that multiplying the numerator and denominator of a fraction by the same quantity results in an equivalent fraction. For example, if we have the fraction 2 over 3, we can multiply this by 1 in the form of, say, 4 over 4, which gives us an equivalent fraction of 8 over 12. We use the same idea to rationalize the denominator of radical expressions. And the goal of rationalizing a denominator is to eliminate the radical from the denominator. So let's start with square roots. We use the fact that the square root of a times the square root of a is equal to the square root of a squared, which simplifies to a, as long as a is greater than or equal to 0. So for example, if we have the square root of 5 times the square root of 5, this will equal the square root of 25, which just equals the radicand 5. So notice how this gets rid of the radical. Therefore, to rationalize the denominator of 1 over the square root of 3, we will have to multiply by 1 in the form of the square root of 3 over the square root of 3. So multiplying both the numerator and denominator by the square root of 3 to give us an equivalent fraction. And the reason we choose to multiply by this value is because this will give us a perfect square as our radicand. So we have the square root of 3 over the square root of 9. And now that we have a perfect square under the radical, we take the square root of 9, which is 3. And now we have an expression simplified with no radicals in the denominator. So let's try a few more examples. For this expression, we can first simplify the radical in the denominator and factor out a perfect square of 9. This then simplifies to 3 times the square root of 2. 36 and 3 have a GCF of 3, so this reduces to 12 over 1. And now the last thing that we need to do is to rationalize the denominator, since we have a radical in the denominator. We can multiply both the numerator and denominator by the square root of 2, which will give us 12 square root 2 over the square root of 4. And now we have a perfect square as our radicand. The square root of 4 is 2, and we have now eliminated the radical from the denominator. It looks like we can also reduce the 12 and 2, which then simplifies to 6 radical 2. And now our expression is fully simplified. For the next example, since we can't simplify these radicals further by just simply using the quotient rule, we will have to eliminate the radical from the denominator by rationalizing. So we multiply by square root of 2 over square root of 2, which now gives us a perfect square as our radicand. The square root of 4 is 2, and now that we don't have radicals in the denominator, we have fully simplified our expression. For this example, it looks like the only way to simplify is by rationalizing the denominator. We can multiply by square root of x over square root of x, which then gives us a perfect square as our radicand. This then simplifies to 2 square root of x over x. And now that we've eliminated the radical from the denominator, our expression is now simplified. So sometimes we will have to use the product or quotient rule for radicals before rationalizing. So for the following example, we can begin with simplifying the radicand, which reduces to 1 over 8. And for a radical to be simplified, we also can't have a fraction as our radicand, so we use the quotient rule and separate these as 2 radicals. The square root of 1 is 1, and then we can simplify the denominator. 8 has a perfect square factor of 4, so this becomes 1 over 2 square root 2. The last thing we need to do to simplify this is to rationalize the denominator. So we can multiply by the square root of 2 over the square root of 2 in order to get a perfect square as our radicand. This then simplifies to the square root of 2 over 4. For the next example, it looks like we can't reduce the fractions in the radicals, so let's apply our product rule, and we can reduce the 7 and the 14, so we have the square root of 5 over 6. Apply the quotient rule, and now we have to rationalize the denominator. So we can multiply by the square root of 6 over the square root of 6, so that our radicand is a perfect square. And this simplifies to the square root of 30 over 6. And since 30 has no perfect square factors other than 1, our expression is now simplified. For this expression, it looks like we can't reduce the fraction in the radicand, so let's apply the quotient rule to separate the radicals. We can simplify the numerator, factor the perfect squares from the radicand, and use the product rule. So the numerator simplifies to 2x square root of 3x. The radical in the denominator cannot be simplified further, so now we will just need to rationalize the denominator. We multiply by the square root of 7y over the square root of 7y, so that the radicand is a perfect square. This then simplifies to 2x times square root of 21xy over 7y. And now our expression is simplified. Now let's go over how to rationalize a denominator that contains radicals with higher roots. So consider the following expression. This time, in order to get rid of the radical from the denominator, we will have to multiply it by something that will give us a perfect cube as our radicand, since this now has an index of 3. So some perfect cubes include the following. And since we know that 8 is a perfect cube, therefore we can multiply this by the cube root of 4 over the cube root of 4, so that we have a perfect cube as our radicand. So this multiplies to 7 cube root of 4 over the cube root of 8. And now we have a perfect cube as our radicand. So now we can take the cube root of 8, which is 2. And now that we have eliminated the radical from the denominator, the expression is simplified. If instead we have a fifth root, the same idea applies. We would have to multiply by something that will give us a perfect fifth power. And some perfect fifth powers include the following. So since 32 is a perfect fifth power, we should multiply the fraction by the fifth root of 16 over the fifth root of 16 in order to get a perfect fifth power as our radicand. This then simplifies to 7 times the fifth root of 16 over 2. So sometimes it may be helpful to use exponential notation to help us decide what to multiply by. For example, in order for 2 to be a perfect cube, we would have to multiply by 2 squared, so 2 times 2 squared, which is 2 to the third power. Or for 2 to be a perfect fifth power, we would multiply by 2 to the fourth power, so that 2 times 2 to the fourth power will give us 2 to the fifth power. So we'll use this strategy when rationalizing. Let's try some examples. For this, since we can't simplify the fraction in the radical, we can use the quotient rule to write these as 2 separate radicals. Now we need to rationalize the denominator, so we multiply this expression by a radical that will give us a perfect fifth power as our radicand. Let's use exponential form. Notice that we can rewrite 4 as 2 squared. Therefore, it looks like the radicand will need to be multiplied by 2 to the third power in order to get a perfect fifth power. So we multiply both the numerator and denominator by the fifth root of 2 cubed, multiply across, and we get a perfect fifth power as our radicand. So we have the fifth root of 3 times 8 in the numerator, which is the fifth root of 24, and the denominator simplifies to 2. Now we have eliminated the radical from the denominator, so our expression is simplified. For the next example, we rationalize the denominators with variables in the same way. In order for the radicand to be a perfect fourth power, we will have to multiply x by x to the third power. So then we multiply both the numerator and denominator by the fourth root of x cubed. Multiply across, and now we have a perfect fourth power as the radicand. So our expression simplifies to 7 times the 4th root of x cubed over x. So sometimes we may have a denominator with a sum or difference that contains radicals. For example, 2 over 4 plus radical 3. To rationalize a denominator as such, we will actually have to multiply by something called the conjugate. The conjugate of a binomial is the binomial obtained by changing the sign between the two terms. So the conjugate of 4 plus square root 3 is 4 minus square root 3. The product will simplify to an expression that contains no radicals. So we multiply the numerator and the denominator by this conjugate. This will give us 16 minus 4 square root 3 plus 4 square root 3 minus the square root of 9 in the denominator. So the middle terms will cancel out, and the square root of 9 is 3. 16 minus 3 is 13. And the numerator simplifies to 8 minus 2 square root 3. And now we have eliminated the radicals from the denominator. So our expression simplifies to 8 minus 2 square root 3 over 13. Let's go over some more examples. For this, since we have a radical in the denominator, we will have to rationalize it. And since there's two terms, to eliminate the radical, we will have to multiply by the conjugate, which is 5 minus square root 3. And doing so will help us remove the radical from the denominator. So we multiply this out and simplify. We have now eliminated the radical from the denominator, and our expression simplifies to 15 minus 3 square root 3 over 22. And for the next example, again, since we have a radical in the denominator, we will have to rationalize it. And to do so, we need to multiply by the conjugate, which is the square root of 5 plus 1. So we multiply both the numerator and the denominator by the conjugate, simplify and combine like terms, and now we have removed the radical from the denominator. So our expression simplifies to 9 plus 5 square root 5 over 4.